Alright, hello math physics, Stuckel here. We're going to be doing some brief video notes on the last parts of Freefall today. So let's go through, start talking about this, see what all this looks like. What I'm going to need you all to do first is turn to page 24 in your book. Ideally, looking something like this. We see up here, top page right here, here. Again, we are on page 24. So everyone please get to page 24 and put yourselves there. Alright, everyone there. Question number 1. We did this already. This was the experiment we did. We did this. We got our acceleration due to gravity as 9.8 meters per second squared. Now I'm going to put the negative there for here. We're going to talk about this. This is going through with what we're doing today. But just note, a negative is here. Kind of. Asterisk there. We'll talk about this as we go today. We're going to skip question number 2. You may do question number 2. It is a good practice problem, so that might be something you want to do when we have time to do homework today. Look at that, potentially. But today, in this video note specifically, I want to go over question number 3, because question number 3 of all the questions is the one that's the most challenging and the part that I want to deliberately show off the most. So let's talk about this. I'm going to zoom in. Bwop. A parachutist jumps from a height of 6,500 meters and falls freely for 15 seconds. She then opens her parachute and over the next 20 seconds slows down with an acceleration. We'll ignore that word. So an acceleration of 7.1 meters per second in the opposite direction. After that, she falls the rest of the way at a constant velocity. What is her velocity just before the parachute opens? What is the velocity of the girl as she strikes the ground? And what is the entire time of her descent from the plane to the ground? So let's get answering these. And before we answer any of these questions, we are going to do what we should always do when looking at a thing like this. We're going to graph this. Here's our xt graph. Here's our vt graph. And here's our at graph. So, at graph is too low. There we go. At graph right there. So, let's quick check on this. First things first, our acceleration over time. What this question is really going to do is it's going to challenge our thoughts on what is the positive and what is the negative direction for all these things. Let's make a brief decision right here. Since this is video notes, usually we decide this as a class, but since this is video notes, I'm going to decide for us. I'm going to point up this way. I'm going to point down this way. I'm going to say downward is negative and upward is positive. These are important. We're going to follow these lines of thought the entire way through as we go through this. Let's start out, as we always should, with our VT graph, as those are the most generally easy to conceptualize, think about, and understand from a certain point. Let's think about what's happening here. This parachutist is jumping off of a plane and falling as she goes downward. In other words, she's going in the negative direction. Her velocity, her speed, should be in the negative sort of direction. Let's recall that velocity, our v, if we turn back 1, 2, 3 pages, back here, our velocity right here, its only difference between speed and velocity is that the velocity is the speed and direction that something is moving. So we have to take this direction into account. Here, back on this problem, we're going to be taking this velocity into account by this direction into account for our velocity by keeping track if our velocity is positive or negative the entire way through. So we come over here and we go, well, at the beginning of this trip, for the first 15 seconds, we're going to be speeding up in the negative direction. We're increasing our speed as we go. Then, if we look at this point, she opens her parachute and for the next 20 seconds slows down. Well, that means that between here and 35 seconds, we are slowly decreasing our speed. We're getting closer to a speed of 0 as we go. After that, she's going to keep at a constant velocity the entire rest of the way. Note how that velocity is still negative. We're still keeping this velocity negative, but we know it's constant for that way. If we look down at our acceleration versus time graph, this is going to give us some nice little hints that we can do. This first part, our VT graph, has a negative slope. This is going to go to our acceleration. We're going to have, for the first 15 seconds, a negative 9.8 meters per second squared acceleration. Note how I'm getting this, because we are falling freely. This is our assumption of free fall. Assumption. So our A is negative 9.8 meters per second squared. Note again that I'm putting the negative here, and I hope now we can see why I'm putting the negative here, because in our case we are accelerating in this negative direction. That is where that negative is coming from. Then, as we're going here, we are now at a positive slope for our velocity. We are increasing in our velocity like this. That means our positive slope here should be right here, and I think it should be at a positive 7.1 meters per second squared. Finally, we're going to go constant for the rest of the time after this 35-second mark, so we'll go down to this last part. Okay, we have our acceleration, we have our V. Let's look at our XT graph. Our XT graph, we're going to start at 6,500 meters. We are going to increase in our speed over the first 15 seconds. We are going to decrease in our speed over the next 20 seconds. And then finally, we're going to keep that speed that we had at the end of there for the entire way down constant until we hit the ground. We don't know what that time is, but we know that that is going to be our trip. Okay, graphing done. Lovely. We know what this all looks like. So, cool. Great. This looks great. How are we going to actually solve these problems? Well, let's look at this. The first thing that it asks is, what is her velocity just before her parachute opens? Well, we go to our questions. We see that we are falling freely for 15 seconds. We're jumping from this height. Note right here, I'm starting at a velocity of 0. Let's put some terms to these things. We're going to need some specific spaces. This is part 1 of the situation, when we're falling freely. We have part 1, part 1, part 1. During part 1, our V1 is equal to 0 meters per second, as defined right there. We don't know what our x is. We should maybe calculate that. Our V2, that is what we are looking for here. We are looking to see what our speed is just before the parachute opens. We know our acceleration is negative 9.8 meters per second squared, and we know that our time is 15 seconds. Okay, lovely. Well, we have all this. Let's calculate that V2. Why don't we? So, we come over here. We know all these things. We then know that V2 is equal to AT plus V1. And then we can go through and do this calculation out. Well, our V2 is equal to negative 9.8 times 15 plus 0. So we just do 9.8 times 15. Doop. And we get 147. V2 equal to 147 meters per second. Note again, we are keeping this free fall assumption in this. So our acceleration is constant the entire way through. Note as well, I should have a negative in front of this 147. That will be specified right here. Negative 147 meters per second. That is our V2. I also know where this problem is going. So while this right here is the answer to part A, I'm also going to calculate the distance we're traveling and that x, as long as we're here. The easiest way to do this is with equation 2, VI plus VF times t. As we know, VI is 0. We know our VF now is negative 147, and we know our t is 15. We can come over here, plug all these in. 15 divided by 2 times 147. Boop. We get that our x over this case is 1102.5 meters. This is good to know, and we're going to keep it right here as our little piece. In part 1, this is how much distance we have fallen. Lovely. If we note then, this right here, this speed right here, our V2, that is our starting velocity during part 2. So when we go to part 2, our old final velocity is going to become our new initial velocity, and we'll have a different final velocity. Note that the next part of the question, what is the velocity of the girl as she strikes the ground? That's the velocity right here, any point along this constant line. Note that we could do the end point when she actually hits the ground, way over here, or we could find it right here at the end of part 2 when she's starting to go at that constant velocity. So let's just do that one. That sounds easier to me. Part 2 then. Boop, boop. We know that our VI is going to be negative 147 meters per second. That is our given information. We know that we are going to spend 20 seconds on this. We're looking for our VF. So our T is going to be 20 seconds. And we additionally know our acceleration. Here's the first big thing we really have to think about, because here we have a negative acceleration because we are going downward. But now this acceleration is slowing us down. Our slope and this right here point to a positive acceleration in this case. We are increasing or getting more positive with our velocity. So we're going to have to write that there. This is going to be a positive 7.1 meters per second squared. All right, lovely then. So we have this, we have this. We are also going to want to find x here. Spoiler alert. We'll talk about y in 1 second. But let's come here and let's figure out what this all ends up as. Specifically, let's find our VF. Note how we have the same set of variables that we'd like to use in this case. So let's use equation 1 again here. VF is equal to AT plus VI. We come here and we go, well, our VF is equal to 7.1 times 20 minus 147. 7.1 times 20. Not 71, 7.1 times 20. Boop. That's 142. So we get that this is 142 minus 147, which gives us negative 5 meters per second. Lovely. Perfect. This is going to be then our VF. So we have that there. This right here is her velocity as she strikes the ground. So far we have our answer for A right here. is going to be negative 147 meters per second. Our answer for B is going to be negative 5 meters per second, as this is the velocity she will stay at until she hits the ground. There's no more acceleration after this point. All we have to do then is answer C. And note how this right here is asking for the entire time of her descent from the plane to the ground. It wants this time right here, the time it takes for her to reach a position of 0. Let's note, it takes her 15 seconds to get here. It takes her 35 seconds to get here, and then it takes her some unknown amount of time to get all the way over here. How do we find that? Well, she's moving at a constant velocity, so x is equal to vt during part 3. So we could scroll down here even, part 3. In part 3, our equation is x equals vt. We know our velocity. We know how fast she's moving along this track. We just calculated it. V is equal to negative 5 meters per second. We know we're looking for our t. This is what we're aiming for. What we don't know is the distance that she travels over this time. And this right here is what we're going to have to go back to those earlier parts and get some more information on it with. So we come here and we note that we traveled this far originally in part 1. In part 2, we can do that same calculation. We can come over here, use this equation, x equals 1/2 vi plus vf times t. We know all of these things now, so we can just plug them into each other. 147 plus 5 divided by 2, make it negative, and then multiply it by 20. We get a solid x is equal to negative 1,520 meters. This brings up an interesting point that I definitely forgot to do earlier. Our velocity here is negative 147, so our position here should also be negative. If we think about this, our displacement is also downward, so our displacement should also be negative here. Okay, lovely. We have these then. We know right here on our graph then that this point right here, the point that marks the end of part 1, well, this happens at 6,500 minus 1,102.5. Or we could say it's somewhere around 5,400, approximately. We know that this point right here at the end of part 2 is exactly 1,520 meters below 5,400 meters. This gives us somewhere around 3,900 meters. Somewhere around there. Close enough. We'll do the actual math and calculate that out, but that gives us the distance we are going to fall between here and here. It should be somewhere right around 3,900 meters. Well, let's get back to this then. Here. Sorry, I keep on turning off the dock cam. So we come back over here and we go, well, let's look at this. We have this. We have this now. It's this plus 102.5, boop, minus 6,500, boop. X is going to be 3,877.5 meters. We know that this is going to be falling that amount, so we're going to be going negative that amount as we go through with this. So now we can calculate for our t. We know that it's this plus this, or this divided by this. X divided by v is equal to t. So we take our x number divided by that, divided by 5. And we get a solid time equal to 775.5 seconds. Now note, this is this plus the 35 seconds it takes to get to the beginning of this to be the total time. So we'll take this and do t total is equal to 775.5 plus 35. And we can get that our total time right here is equal to 810.5 seconds. Assuming I did all my math right. We'll believe in that. All right, so this is kind of our extremist point. This is as far as we're going with the Freefall at this moment. We can do more with Freefall. I hope that you will begin the homework and start going into that, looking at Freefall from there. One thing I would like you all to try is going through the homework right now and kind of talking through all these things. There is additional stuff we could do with Freefall, and we'll talk about that. It won't appear on the test, but it'll be useful going through and talking about in later units. So we'll check back on that and see what our thoughts are next class as we kind of go through this. But for now, this is kind of where we'll end off. Specifically, multi-part problems like this. Remember our steps that we use to go through them. You graph the situation. You do the math part by part, having different variables for each part. So different things here, different things here, different things here. You make sure your directions are properly labeled in terms of their positive and negative. And then from there, you just use a combination of your graphs and your math to get any information. This is confusing. There's a lot of stuff in it, but I believe in you. You'll do fine. There aren't too many problems in the homework that are as challenging at this, but I would recommend you try them out. We'll talk about this more next class. So yeah, spend the rest of your time, do some practice on this. I hope your quiz went all right, and I'll see y'all on Friday. Have a great day.